Good morning, everyone. Welcome to lecture 2 of remote sensing and GIS. And today we will explore session and their application, sensors and their application in remote sensing. We will begin with a brief recap of remote sensing fundamentals and gradually move into how different type of sensors capture information about Earth's surface. Remote sensing is the science of obtaining information about objects or areas from a distance without making physical contact. Just like how our eyes detect colors, shapes without touching an object, sensors on satellite do the same but in a more advanced quantified way. Okay, then what is wave? To understand how remote sensing works, we must first understand waves. A wave is simply a disturbance that carries energy from one place to another. Light, sound, ocean waves, we can get those examples. In remote sensing, we are especially interested in electromagnetic waves as they are the medium through which energy travels from the earth to the sensor. So every wave has two key properties, wavelength and frequency. Wavelength is the distance between two crests, while the frequency is how many waves pass a point per second. These two characteristics determine the behavior of electromagnetic wave and how sensors interpret them. The electromagnetic spectrum is the full range of electromagnetic radiation from radio wave with a very long wavelength to gamma rays with extremely short wavelengths. Every object reflects or absorbs energy differently across this spectrum, and that unique pattern helps us identify materials remotely. So here you can see the image of electromagnetic spectrum, the size comparison also there. Here you can see the radio waves. It may be 10 to the power of 3 sometimes, and it's a wave, the actual size like a building, or a microwave. It's into the 10 to the power of minus 2. That means centimeter level. Likewise, up to 10 to the minus 12 gamma rays uh, compared to atomic nuclei. So that is the range of wavelength range in the actual sense. But the visible spectrum, when we talk about the visible spectrum, although the electromagnetic spectrum is vast, the human eye can only detect a small portion from about 350 to 700 nanometers. And this is the visible spectrum. The color we see, red, green, blue, are just a tiny portion of the available electromagnetic information. So you can see here when we see, we can see the electromagnetic spectrum. So it's very tiny portion of here visible spectrum. Here we can see green to or the blue to red. It span over blue to red. It is very tiny portion of visible spectrum in the electromagnetic spectrum. So the objects appear in different colors because they reflect certain wavelength of visible light. In real life, we can see many objects in a different colors. For example, a green tomato in this picture, red when ripe because it start reflecting more energy in the red wavelength region, around 650 to 730 nanometers. That is why we can see red as a this ripe fruits as red color. So then this leads us to an important question. If we detect changes in the visible spectrum with our eyes, what about changes that occur outside this range? What information could we gather if we were able to detect invisible wavelengths like infrared or microwave energy? And this is the foundation of remote sensing. Then let us now move into application. Vegetation absorbs most of the red light that hits it but reflect green light. This is why healthy leaves appear green. So we know when we see outside, so we can see the color of a tree or leaves, it's green. Because of it appear green, it reflect green and absorb other colors. They also use wavelength between 400 and 700 nanometer for photosynthesis, called photosynthetically active radiation. So this, so the region that absorb in leaves are um, except green color, they are absorbed, and they those radiation they use for photosynthesis. So it is then we can understand the reflected green light. We can detect some properties of leaves when we uh, when we are really working with the that spectral range. So here now you can see this image. So this vegetation and soil. So in vegetation, they are absorb blue, green, red mostly, but they reflect a near infrared compared to the red, green, and blue color. Here, green are somewhat sharper. That's why we can see the vegetation most of the time green color. But compared to this one, they are reflected more near infrared wavelength. So it is when we want to analyze or identify the vegetation more clearly, instead of red, green, blue, we can use near infrared wavelength, and we will discuss this in later slides also. So interestingly, healthy vegetation also reflect large portion of near infrared light due to the structure of leaf tissues, especially in spongy mesophyll. This region of the spectrum is invisible to our eyes but crucial in identifying plant health. So near infrared, we cannot see this region, but if we have a good sensor to capture those electromagnetic wave, so we can clearly identify this region, this plant health, we can clearly identify the plant health of uh, using the near infrared region. Here also, so as you can see, the near infrared region, it has more increase in this region more rather than this region, so that then we can by analyzing, by getting this near infrared wavelength, we can clearly see this region also. So if we can get the information on this region, so we can clearly get uh, get the idea of plant vegetation analysis. We can do that very effectively. So I have prepared some video from YouTube.
It provides information about the ability of a sensor to distinguish between the ranges of the electromagnetic spectrum. The spectral resolution of a sensor increases with the number of channels in which it can receive ranges of the electromagnetic spectrum. The sensors used in remote sensing record wavelength ranges in specific spectral channels. But what happens next? The information captured by each channel is stored as a grayscale image. In each grayscale image, the intensity of the reflection in different areas of the Earth is recorded for the specific wavelength range of that channel. What does the reflection intensity of surfaces, which we see in the grayscale image, tell us? A couple of things. But first, we need to understand that different materials have unique spectral signatures, meaning they absorb and reflect light from various wavelengths differently. We can distinguish objects from one another by looking at their reflection behavior. Sensors with more spectral channels allow us to see the spectral signature of an object with more precision. This also makes it easier for us to separate objects from one another. By using the spectral signatures, we can differentiate between healthy and stressed vegetation, as they have different absorption behavior. Most Earth observation satellites are equipped with multispectral sensors. Modern multispectral sensors, such as the MSI on board of Sentinel-2, collect information in many channels, in this case 12. If one looks closer at the wavelength ranges, we can see that a channel doesn't just correspond to one wavelength. Instead, it picks up a specific wavelength range and averages its information. This is necessary because the signal obtained from multiple wavelengths is much stronger than that of a single wavelength. In addition, not all channels are adjacent to each other. So sometimes there are large gaps of wavelength ranges in the electromagnetic spectrum in which no information is collected. This is because the atmosphere doesn't allow certain wavelengths to pass. So we must place the channels in so-called atmospheric windows, where the wavelengths can penetrate the atmosphere and be reflected to the sensors. Ultimately, the field of application determines the ranges in which the spectral channels are located. Although the spectral resolution of multispectral sensors has risen in recent years, much information about the properties of surfaces is still unknown. Modern hyperspectral sensors are about to close these gaps. Hyperspectral sensors have several hundred channels and thus a very high spectral resolution. They continuously cover a much larger range of the electromagnetic spectrum, but to get this technology into space is complicated. Therefore, sensor systems such as the ISS DESIS, which observes the Earth in 240 channels in the visible and near-infrared range, are still pioneers in this field. However, the opportunities presented by hyperspectral imaging are promising, and the first operational satellite systems with this revolutionary technology are about to be launched.
So remote sensing works by capturing specific wavelengths of reflected energy. Sensors isolated selected wavelengths create multiple spectral images. Each pixel in these images represent a reflectance value for a particular spectral band. So here you can see the multispectral image. It's a, not it's a false color image. So you can see then some areas are red and some areas are green. Here green are more uh, healthy vegetation, and red areas not that much healthy. So we can clearly distinguish this by using these spectral images. So reflectance data can be collected from three levels. As you can see, satellite, drones, and handheld devices are here. So handheld devices we use at a ground level, and drones we can use 20 to 150 meter range, and satellite also maybe hundreds of kilometers above the Earth's surface. They are getting information. So each platform are defined spatial accuracy, coverage, and ease of data collection. They are different. So we are refreshing our knowledge in previous lecture. Also we discussed this one, vector and raster data. And data used in remote sensing can be categorized into these two structures, raster and vector. And for your understanding, raster data is grid-based imagery, such as satellite photos, and where each pixel carries a value. Vector data, on the other hand, uses point, line, and polygon to represent discrete features like building, road, boundaries. So we were discussed this last lecture also. So for your just recap, when we talk about the raster data, uh, RGB satellite imagery captures visible red, green, and blue bands, as you can see. So these three bands create this color image, and each pixel contain value for each color, and when combined, they are form the full color image. So these three band combined, red, green, and blue, will create this image, the color image. So beyond this RGB imagery, we have multispectral imagery also, where each image contains several separate bands captured at different wavelength, including infrared. In this grayscale example, each pixel represents the reflectance at single band, such as near infrared, and darker or lighter tone shows how much energy in reflected form the surface. So you can see here low value is 0 and high value is 255. So here the value is sharper, means high value, and some areas darker values. So it has less reflectance in this region. Also, we discussed last time uh, the raster data, the resolution. What are the resolution we talk about in the remote sensing? Remote sensing sensors is defined by four type of resolution. As you can see, spectral resolution, refers to the number and width of a spectral bands. Radiometric resolution is the sensitivity of the sensor to detect variation in energy, and a spatial resolution determines the size of each pixel on the ground, and the temporal resolution describes how often sensors revisit the same area. So this slide for a small recap, and we also talk about the vector data. Vector data contains of point, line, and polygons. This format is ideal for mapping infrastructure such as building, road, and administrative boundaries. So one major advantage of vector data is scalability. Yeah, here, if it in a raster data, if you are scale down, so you will get this pixelated uh, image. But in vector data, whatever you are zooming, so you will get like this very clear quality image. There are two application in raster and vector data. We will discuss those things in later in lectures. So this one is our today's lecture in multispectral, hyperspectral, and thermal sensors. So we are moving into this. The understanding of the three main categories of remote sensing sensors, especially multispectral, hyperspectral, and thermal sensors. And this will help us to understand how each type collect data and where they are applied. So we are move on to the next slide. So first, we talk about the multispectral sensors. Multispectral sensors are passive sensors that detect reflected sunlight from Earth's surface. They typically capture 5 to 10 broad spectral bands, mainly in visible, near infrared. Visible, we have three bands: red, green, blue, and near infrared, short wave infrared region. Those sensors provide good spatial resolution and are widely used in land mapping, vegetation monitoring, and environmental studies. So here, uh, this one is Landsat series. Here are some. These are widely used in multispectral satellite system. Landsat mission with 30-meter resolution, and so they have 50 years of archive. Everyone can access this Landsat data, and you can even download this data freely available in your research. Also, you can use this data for free, since it is freely available in the internet. And another multispectral satellite, Sentinel-2, it can capture up to 12 spectral bands um, and goes up to 10 to 20 meter resolution. And this one is Spot series, known for high spatial resolution and push broom. Then they use push broom scanning method, their satellite. So is Spot also a series of satellite. In 2014, they launched Spot 7 satellite also, and it has 1.5 meter ground resolution. So now the performance of multispectral sensors largely depend on its spectral resolution, how many band it can record, and how wide or narrow they are. The key spectral region include visible, natural color, and soil information, near infrared for vegetation, and short wave infrared for moisture content and mineral detection. So as you can see, so those are different, combined with different bands, false color images, and one true color image. So there are visible range, near infrared, short wave infrared. So getting these separate bands, we can analyze natural color, soil, haze, vegetation, reflectance, moisture, minerals. So we can use several applications for those images and get the information on those areas. So I prepare a table to summarize these things. This table summarized wavelength ranges, corresponding Landsat sentinel bands, and what information they provide. For example, the near infrared band around 0.7 to 1.3, 0.7 to 1.3 near infrared band in micrometers is visible for detecting healthy vegetation, distinguish land from water bodies, and this one short wave infrared bands help detect vegetation, moisture, geological mineral mapping. Uh, Likewise, so you can understand and get the idea of how this spectral region and how they can uh, diagnose some get some information from that spectral bands. Multispectral data is stored as a raster layer, as we discussed earlier. What is raster? Each band is separate layer containing pixel values. As you can see here, there are 7 bands here. 2 is green, 3 red, 4 near infrared, 5 is near infrared, 6 is the thermal infrared, 7 is mid infrared. First one, blue band. So red, green. When we stack this band, we can create useful visualization. A true color composite, the first one, true color composite, red, green, blue. Then the uh, false color composite with a near infrared. This one is false color. False. This one is false color, and this is pseudo natural color composite 352. False color 432. This one is 321. So here I also download and attach this video from YouTube.
When we investigate land cover using the instruments aboard Landsat satellites, we collect sets of data for different wavelengths. Some are in the infrared, and others correspond to blue, green, and red visible light. We can combine any 3 of the images to create different depictions of Earth's surface. What you're seeing now is a Landsat image of Florida, made with data from the blue, green, and red visible wavelengths. We call this a natural color image because it looks approximately like what we would see with our naked eye. We flew far above Florida. But we could choose data from other wavelengths and map them to blue, green, and red colors to highlight different features of the land surface. With this particular depiction of the multispectral data, for example, we can see much greater contrast between trees and shrubs in sawgrass marsh than was apparent in the natural color image. We call certain combinations of wavelengths false color images because they do not replicate what we see with the naked eye. Yet they allow us to create images where we can highlight or enhance different surface features. The following depiction approximates the type of image that you can get from color infrared film. It turns out that vegetation, growing active vegetation, reflects a lot of light in the near infrared, and so areas with healthy growing vegetation jump out as red in these images. You can easily distinguish the healthy agriculture more clearly than you can in the true color image. Here you can look at the 3 different depictions of the multispectral data we used to create these images. And you can see how the surface cover appears different with some features enhanced in the different depictions.
So multispectral sensors are used in wide range of practical application, as you can see on the previous video also. We can use this for urban growth monitoring, land use classification, change detection over time, and vegetation health analysis, flood mapping, water body extraction, mineral exploration, also GIS based advanced visualization. So we can use several application multispectral sensor data. When we talk about the urban growth and land mapping, one of the most common use of multispectral imagery is analyzing urban expansion and land use. Land cover refers what physically exists on the ground, like vegetation, water, or built-up areas. Land use refers to how humans used that land, something like residential, commercial, agricultural, likewise. So tool like NDBI and QGIS semi-automatic classification plugins help you can classify urban areas using these tools effectively while using these multispectral images. When we talk about the temporal analysis and change detection involves comparing satellite images from different years. So methods like image subtraction, image division, and color composite overlay help highlight areas of change. Techniques such as change vector analysis in CVA can measure both the magnitude and direction of spectral ranges over time. So in temporal analysis, you can have 5, 10-year apart 2 images, and simply you can subtract those image to get the find the changes happen in those 2 images. Simply you can subtract it, since because image is a 2-dimensional array of numbers. So you can use mathematical equation. Simply you can subtract, divide, or add, or whatever you can do for a simple matrix calculation you can do. In vegetation health monitoring and agriculture, we will discuss this deeply since multispectral images most of the time talk about this vegetation health and uh, mostly widely used for the agriculture. Healthy plant reflect a lot of near infrared lights and absorb red light. So that's why they absorb red light and emit green light. So we can see plant as a green. When plants are stressed due to a water shortage, nutrient deficiency, disease, or pests, these reflectance patterns change. So uh, by detecting this variation early, a farmer can take action before visible symptoms appear. So this slide visualizes how different stress factors affect crop health, water deficit, nutrient deficiency, disease, toxicities. All of these reduce the plant's ability to perform photosynthesis. So using remote sensing, we can detect these stress signatures. We can from space or drone by using drone we can before this situation becomes severe, we can detect this situation early, so we can do some remedial action for that. So here you can clearly see the difference between healthy and unhealthy vegetation. Healthy plants have high reflectance in the near infrared region and low reflectance in red band. So this is healthy. So in near infrared, it has higher intensity, and unhealthy or stress vegetation shows the opposite. So you can see stress or unhealthy dead leaf. So spectral reflectance different from healthy leaves. So here also for your understanding. So in a single tree also you can see there may be healthy, unhealthy leaves there. So you can clearly get the idea of by using the multispectral remote sensing images, you can get the idea of how this vegetation healthy or unhealthy. We can get those information from these multispectral images. So we are move on to to quantify plant health. A scientist developed mathematical formula called vegetation indices, and these indices represent the ratio of reflected light between different spectral bands. They provide simple yet powerful way to evaluate plant vigor and stress across large agricultural areas. So the vegetation indices allow us to measure plant response through the growing season. Most of these indices rely on reflectance values from visible and near infrared bands. They offer valuable insight for precision agriculture, irrigation planning, and early stress detection. So next, what is this vegetation indices? The most widely used vegetation index is NDVI, mean normalized difference vegetation index. So as you can, the NDVI is equal near infrared minus red region. So these two bands, near infrared band minus red band, and it divided by near infrared plus red band. So here, if the vegetation is healthy vegetation, near infrared minus red gives more value to this equation. So the anyway this near infrared minus red value and near infrared plus red value always less than 1, since this one is greater. So the vegetation high values due to near infrared is high. So value from this will range between -1 to +1. So there are higher values indicate healthier and dense vegetation. And the NDVI, this value is higher. That means the vegetation is more healthier than the one that value has less value. NDVI values in the plus indicate dense, healthy vegetation. Around 0 represent bare soil or very sparse vegetation, and negative value indicate water, built up area or cloud. So this makes NDVI a quick and effective monitoring tool for agriculture fields and forest. Yeah, this slide also simply illustrate how the NDVI looks like. So this healthy vegetation got 0.72 value, and this stressed vegetation got 0.14. If this NDVI is 0, then what is the meaning? It means this most probably it is not a vegetation, it may be a bare soil or just ground. So you can see this, this is vegetation index. After we map this vegetation index, so we can get this right NDVI map. It shows spatial variation in vegetation health across the field. Darker green areas show high NDVI values. That means it's a healthy vegetation, healthy crop. By using these values, farmer can apply fertilizer, irrigation, or pest control precisely where needed. So this will industrially farming, when someone industrially farming large area, so he can use this data. So he need to concentrate on this region, this red region. Then this green region are healthier, so he don't need to waste his fertilizer or irrigation water for this region. So although this NDVI is powerful tool, it has limitation also. It defines where a problem exists, but not the cause. For example, a low NDVI value, earlier we have seen that image also, could be due to a drought, disease, or nutrient deficiency. Therefore, NDVI is excellent for detection, but not for diagnosis. So we have to mindful about that. Then the water bodies generally show negative NDVI, as I discussed previous slide. This makes it easy to detect lakes, river, and flooded areas. Advanced indices like NW, NDWI, and MNDWI are used to highlight water more clearly. There are NDVI is one indices. There are many indices in the NDWI, MNDWI likewise. So additional digital elevation model, TEM, so helps simulate flood behavior, drain pattern, and water flow pattern. So those the digital elevation model also it can be used for identify water patterns, behavior, and water flow. So those can be identified using digital elevation model also. So we are moving to next application, multispectral imagery. This one is geological and mineral exploration. Remote sensing is also widely used in geology. The short wave infrared region, especially 1.3 to 3 micrometers, is ideal for identifying minerals. Clay mineral and iron oxide display distinct reflectance signature in specific uh, shortwave, infrared, and visible bands. Multispectral and hyperspectral data are used to map geological formation and mineral-rich zones. So remote sensing data becomes much more powerful when integrated with GIS techniques like band stacking, true or false color composite, like we discussed earlier, contrast enhancement, and decolor, correlation is stretch, improve visual interpretation. There are many techniques to improve the visual improvement while using remote sensing images. Image fusion method also there. So those things we used in advanced visualization uh, by using GIS software, and also we have remote sensing softwares. Those softwares can use to enhance images. While integrating GIS, you can do some tools like buffering, clipping, union, zonal statistic can be done using uh, GIS tools. So, previous lecture, I also said that GIS and remote sensing are complementary. So the GIS software or GIS system can store, manipulate, and do several things in remote sensing images like raster images, like this one, multispectral images. So it has a capability to visualize, analyze remote sensing data. When we talk about the advantages and limitation of multispectral sensors, multispectral sensors offer good spatial resolution, high signal to noise ratio, and long-term historical data archives like Landsat. So, however, they have limitations such as mixed pixel and lower spectral precision, which may lead to confusion between similar features. Uh, some the spectral confusion. So this happens due to few broad bands. Some band, like earlier video also, you can see you uh, you you saw earlier video also. Some bands they are quite large compared to other bands. Region the spectral electromagnetic spectral region. It's, and sometimes these two bands may overlap one another. So just because of that, there are spectral confusion can happen. So since there are spectral signature for certain object, like when we, as example, if we take soil, uh, soil has a spectral signature. Some bands are much sensitive to soil, some are not. Then the same thing can happen soil or another object also. If it is a built up area or a building also, same can happen. So this uh, by analyzing those spectral range regions, we may confuse, uh, we are classifying those areas as built up area or bare soil mistakenly. So mixed pixel also can happen uh, in a spectral multispectral sensors. We have to keep in mind that when we use in this multispectral images. So this slide also suggests useful visual aids, strengthen understanding, such as spectral reflectance curve of vegetation, comprise comparison tables between satellite sensors like Landsat and uh, Landsat and Sentinel band comparison, uh, uh, diagrams like RGB or false color composite diagram, and NDV example images. So those are we discussed already. I have shown this diagram um, and tables, the reflectant curves also. So this NDVI map in agriculture field. So it can we can get clear idea on how this multispectral images work. We can get this idea. So now we are move on to the other topic, that is hyperspectral sensors. So unlike multispectral sensors, these hyperspectral sensors capture only a few broadbands. Hyperspectral sensors, um, then multispectral sensors capture few broadbands, sometimes eight, uh, 8 to 10 or 8 to 15 bands. But hyperspectral sensors capture hundreds of very narrow bands, the providing continuous spectral signature for each pixel. So you can see that in this image also, there are many bands in a single image. So hyperspectral image has more uh, memory power. They consume more memory power, um, since a single image has maybe 100 to 200 layers. In For your understanding, RGB or normally we see the RGB red, green, blue image, like we our photograph also has only 3 layers. Uh, Imagine if there is 100 layers of a single image, how it massive compared to its memory capacity. So hyperspectral imaging system, also called imaging spectrometers, record hundreds of bands, each around 10 nanometer or less in width. This high spectral resolution allows us to distinguish even subtle difference in materials and vegetation. Why we do this one? Because in a multispectral we have few problems. One that we call that earlier, we call it spectral confusion. So avoid this spectral confusion. So we can use hundreds of layers, so we can clearly get the this kind of a curve, continuous curve. So we have every data on each and every wavelength band. This is wavelength, and this is this axis shows the reflectance. So you can see we can get the continuous graph in hyperspectral images. So we have every data, every wavelength we have a data, so we can clearly draw this graph. It's like this one like a DNA test, or like a fingerprint. So each object, or soil, water, vegetation, has different pattern of wave, as you can see, the different wave. So one that has a knowledge, then he can clearly say this one is this area has soil, this area has water, and this is a vegetation area. So it clearly identify by making this graph. So you can see that it's already we can understand that there may be clear evidence that this water and this area soil, this area vegetation. But in reality, when we use satellite images, and you may not see like this way, so it is very important to identify this pattern, and you can identify this object very clearly. Since let's see this, you want to find the mineral, or let's see, you want to find graphite or something in here, or some phosphate or something. So it has some unique graph like this way, separate graph. So then we can map the area where the phosphate are located. So you can easily use those data for mining. So hyperspectral data is organized into what we call a data cube. It has 3 dimension, x, y for spatial dimension, and the third dimension lambda for wavelength. Each pixel contains full spectral signature across wavelengths, enabling precise material identification. I have downloaded one more video from YouTube for your understanding.
When we see the world around us every day, we are able to recognize most of the things by their color. This is because our eyes can sense the reflected light from any given object and can get a rough idea of the material and composition of the object. However, our perception is limited to what meets the eye. To truly unravel the depths of our world, we must see the world through a different lens, and that is hyperspectral imaging. Hyperspectral imaging is a transformative technology that unveils the intricate behavior of light and gives us hidden, useful information about our world. To understand hyperspectral imaging, you first need to understand how traditional cameras work. Traditional color cameras are similar to our eyes. Their sensors capture only 3 primary colors of light: red, green, and blue. And therefore what we see is the combined value of these 3 wavelengths. The next step is multispectral imaging, where we can get 10 to 20 wavelengths of light, having more information than a normal RGB image. But hyperspectral sensors go beyond this limitation, dividing the light spectrum into hundreds of numerous narrow and contiguous bands, capturing detailed information from visible to short-wave infrared spectrum. Each pixel in a hyperspectral image contains a spectrum of information, revealing the unique fingerprint of the materials or objects within the scene. It can also be called a reflectance spectrum, and by analyzing these spectral signatures, scientists can discern subtle differences that elude our naked eye, unlocking a wealth of information about our environment. One of the greatest benefits of hyperspectral imaging lies in its ability to improve our agriculture industry. By analyzing the reflected light from crops across multiple wavelengths, we can detect stressed crops, identify nutrient deficiencies, and optimize resource allocation, ensuring food security and minimizing the ecological impact of farming practices. We can also study the unique spectral fingerprints of harmful pollutants and mitigate environmental hazards more efficiently. It allows us to protect ecosystems, conserve biodiversity, and take proactive steps toward a sustainable future. Moreover, hyperspectral imaging can play a pivotal role in mining crucial resources. It can differentiate between various minerals with precision, help us map mineralogy, and detect valuable deposits more efficiently, saving time and resources, and minimizing environmental impact. The power of hyperspectral imaging lies not only in its technical prowess, but also in the collective spirit of our innovation and collaboration. It's a tool that empowers us to protect, understand, and cherish our planet. And that's what we aim for at Pixel. Using hyperspectral technology, our goal is to unearth problems that are invisible to the satellites today and build a 24/7 health monitor for the planet. To learn more about
So hyperspectral sensors initially, those are used in airborne system, and later they develop in satellite-based system. So this one you can see in this image. This is Avris on airborne. NASA developed this hyperspectral sensor. Use this aircraft carry this sensor, and they while it was success. So then they implement this hyperspectral sensors to this one for this Hyperion satellite also series also. Then also used a newer mission like Prisma, ENMAP. These sensors are used extensively in mineral exploration, vegetation stress analysis, and environmental studies. So the Prisma spectral resolution, as you can see, they use the more bands used in here. So images like this, they can be used for this classification. Classification meaning you will learn in classification in next lectures also. So if you can separate something similar in same region, so you can classify like this is a vegetation or a paddy field. This area is containing paddy field. This is a built-up area, and this is a river or something. So you can classify the area into a built-up area or a vegetation or a forest. Likewise, you can classify. So for the classification also in minerals or whatever the thing, the high spectral sensors images are we used. That is very good in when we work with classification. So we are going to discuss key application of hyperspectral sensors, including mineral and geological mapping. Using short wave infrared bands, precision agriculture to detect nutrient stress and chlorophyll levels, and water quality monitoring by analyzing absorption in specific wetlands. Those some of application in hyperspectral sensors. So we'll dive into deep. So in here, mineral and geological mapping using short wave infrared band. These bands between 2.0 to 2.4 micrometer are particularly sensitive to hydrate mineral. By analyzing reflectance absorption features, geologists can identify clay, carbonate, and iron oxide minerals. So in Aster satellite, data with 6 SWIR bands at 30-meter resolution commonly used in this field. So we discussed NDVI previously. So hyperspectral imaging in agriculture goes beyond NDVI. It helps to detect chlorophyll content, nitrogen levels, uh, leaf area index, and subtle plant stress symptoms. So, as you can remember, the NDVI, or uh, we we just subtract two bands and divided by addition of those two bands. So simply analyzing using two bands. So in here, hyperspectral, there are hundreds of bands. So you can get uh, a spectral signature of a particular place. So you can clearly get this information compared to the NDVI by using hyperspectral images. Techniques like Tessel cap transformation are used to analyze brightness, greenness, and wetness um, of a vegetation. So those words also you can, if you want get more idea on this area, so you can just Google it or ask from a model, uh, chat model, so you can get more ideas on this region. Environmental studies, hyperspectral data helps map water quality, detect pollutants, monitor algae blooms, and analyze land use changes. Water absorbs near-infrared and reflect blue-green wavelengths, while thermal sensors detect changes in surface temperature. Combining hyperspectral digital elevation models enable better flood hazard map analysis. Those things can be done for the environmental monitoring and water quality when we use hyperspectral images. So for the hyperspectral and multispectral, there are this slide I created to highlight the key difference between these two sensors. Hyperspectral sensors capture hundreds of narrow bands, while multispectral sensors capture only 5 to 10 bands. So as you can see, number of band, hyperspectral hundreds to 1,000 band. This one 5 to 10, maybe uh, 20 maximum. Then the spectral resolution, it depends on both spectral resolution very high, 10 to 20 nanometer. This one is moderate. Spatial resolution is hyperspectral is lower, multispectral is higher. So why this happen is hyperspectral. If it is high spatial resolution, so imagine for a single image, there are more memory power required to store this image than this one. So there are 510 bands. So spectral resolution is high. It consumes less memory than the when we use 100 or 1000 bands with lower resolution, maybe sufficient in terms of memory capacity. And then hyperspectral provides detailed material identification, but require complex processing and large storage. So that's why this one we have to. This one is good for provide mineral identification, but they are payoff. So we have to bear that we need to have large storage capacity, and also the complex processing, computing power needs more computing power. In the other side, multispectral is faster, more cost effective, and ideal for routine mapping and monitoring. So in hyperspectral, it is more faster, cost effective method compared with the hyperspectral. So there are advantages and limitation also. Hyperspectral imaging offers precise material identification and detailed spectral signature. However, it is expensive, sensitive to atmospheric condition, and requires expert processing. In multispectral imaging is affordable, easier to process, and suitable for broad land cover application. But it is lack spectral detail and may misidentify material due to broad bands. Due to a size of a band, it may be misidentify the materials. When we think about the real world application, multispectral sensors monitor crop health, irrigation needs, and pests outbreak. Hyperspectral sensors help identify specific nutrient deficiencies. When you come to the environment, used for land use changes, water quality analysis, and pollution detection. Disaster management, multispectral sensors help assess the flood, forest fires, and earthquake rapidly. In geology, hyperspectral sensors are ideal for detecting minerals and rock composition. So in geology and some agriculture application, we can use hyperspectral images. And agriculture, environment, and disaster management, it is more suitable to use multispectral images. Okay, when should we choose hyperspectral or multispectral sensors? So we can choose hyperspectral when detailed spectral information is required, such as mineral mapping or chemical detection, and when advanced processing capabilities are available. So we can also choose multispectral when the goal is operational efficiency, land use monitoring, crop health, or disaster response. We can use multispectral sensors. In conclusion, multispectral imaging is practical and widely used in operational tasks, while hyperspectral imaging is more specialized and suited for scientific or material specific investigation. The choice depends on your objective, budget, and data processing capacity. So, I hope you understand multispectral and hyperspectral. So, we are now move on to the third topic, that is thermal infrared. Unlike visible infrared reflectance, thermal infrared does not measure reflected sunlight. Instead, it measures the heat emitted by object based on their temperature. So this one is different from other two categories. It is not reflected by the sunlight. It's every object has a thermal signature, thermal energy in it. So every object emits thermal radiation. So we can, by getting those thermal signature, thermal signals, so we can map, we can analyze and map those waves. So in this topic, we discuss regarding this thermal infrared images in thermal infrared remote sensing. So as you can see, for your understanding, I again here again put this slide. This is electromagnetic spectrum. So this region is infrared region. So we discuss this region here, near infrared wave to far infrared wave. So most of object emit thermal waves in this region. So we can by using the sensors, we can get the images, thermal images, and analyze and can analyze the image. Okay, so every object absorb and emits thermal radiation depending on its material and temperature. For example, water has high thermal capacity and keeps plants cooler. This property allows us to detect water stress in crop using thermal sensors. So as you can see this image. So here now this this image shows now it is pouring water into this field. So it is now more greener. Then this image shows less water. So that is, we need to again put some water in this field to become like this one. So this is too much water in it. So likewise, we can map this thermal signature. Thermal remote sensing is very sensitive to plant water stress. Plant that lack water heat up faster. Satellite like Landsat have thermal infrared bands, but their spatial resolution is coarser, around 120 meters. So finer details often requires drone-mounted thermal cameras. So this means 120 meter means a single pixel from this satellite image covers 120 meter ground area. So it is somewhat bigger resolution so we cannot clearly identify the crop field. Therefore, there are drone cameras with thermal sensors. So the farmers use those thermal cameras, and they can get these thermal images like this one. Thermal sensors can also be used to study soil properties also. Since different soil retain heat and moisture differently, thermal imagery help identify soil texture, moisture content, and land surface temperature patterns. You can use a drone images, thermal drone camera to get the thermal images and analyze the soil texture, moisture content, and land surface temperature. Those things you can use these images. So as you can see, this one soil properties and structure can also be studied. This is one image get taken from thermal camera. So this one is low in thermal reflectance. Those are high in thermal reflectance. So since soil retain water differently in the here, so you can differentiate and get the idea of the area, and then you can, based on that, you can the farmer or the person who use this thermal images can get a decision how rectify those problems in their field. I have also downloaded one YouTube video for your understanding.
Have you ever wondered about the invisible ways we can observe our world? How we can detect hidden phenomena that our eyes can't see? Welcome to the fascinating universe of thermal remote sensing, a technique that allows us to measure radiation emitting from any surface, be it a forest, a city, or the ocean. Thermal remote sensing operates on two major scientific laws. The first is the Stefan-Boltzmann law, which tells us that the surface temperature of any object radiates energy and exhibits specific properties. This law allows us to understand how different surfaces emit different amounts of energy, enlightening us about their thermal characteristics. The second law is Wien's displacement law. This law reveals the relationship between temperature and the wavelength of radiation. It states that the wavelength of radiation emitted from a black body is inversely proportional to the temperature of that black body. This law enables us to determine the temperature of a surface by observing the wavelength of the radiation it emits. Now you might be wondering, why is this important? Why should we care about thermal remote sensing? The answer lies in the diverse applications of this technique. From geothermal exploration, identifying geological units and structures, to studying urban heat islands and soil moisture, thermal remote sensing plays a crucial role. But that's not all. In hydrology, it helps us understand the distribution and movement of water in our environment. In coastal zones, it aids in the management and conservation of our precious marine ecosystems. And in the field of volcanology, it's invaluable for monitoring volcanic activity and predicting eruptions. One of the most critical applications of thermal remote sensing is in detecting forest fires. It's based on the principle of identifying fire pixels according to the temperature difference between the energy emitting from the surface and the ambient temperature. This allows us to spot forest fires early, potentially saving lives and protecting our environment. Thermal remote sensing also has applications in other areas such as coal fire detection, seismology, environmental modeling, meteorology, military intelligence, and even in studying heat loss from buildings. In conclusion, thermal remote sensing is a powerful tool in our arsenal to understand and protect our world. It allows us to see the unseen, to detect and respond to threats, and to gain a deeper understanding of the natural and man-made processes that shape our environment. So, the next time you hear about thermal remote sensing, remember its power and the vital role it plays in our world.
Thermal sensors, they are passive sensors that detect emitted radiation rather than reflected radiation. They operate mainly in mid-wave infrared 3 to 5 micrometer and long-wave infrared 3 to 14 micrometer regions. These wavelengths provide valuable insight into temperature variation across the surface. So it measure actually this thermal sensors. It measure the temperature for a particular place instead of collecting the reflectance of that area. Thermal remote sensing has challenges also. The signal strength in the thermal infrared region is low. Spatial resolution also coarser. So as you can see, most of thermal images are somewhat blurred. You cannot clearly see the boundary of and sharp boundaries of an object, and thermal sensors are require cooling system to reduce internal noise. If a satellite capture the thermal energy from Earth's surface, satellite itself should have a cooling system. Otherwise, the sensor also affect to the radiation, since it has also a temperature, so it emits radiation. So the sensor should cool down enough to capture all the thermal energy from the surface of the earth. Thermal infrared data is indispensable in environmental monitoring and agriculture, so it is very important when we come to the environmental monitoring and agriculture. Thermal infrared images, we can use those images, and that is very useful, those two areas. So there are major platforms used in thermal infrared. Landsat series, they have TM, ETM plus, and TRS bands, 6 4 surface temperature. Astra satellite has band 10 to 14 for thermal mapping. MODIS, widely used global temperature and climate monitoring. MODIS is a satellite, weather satellite. This weather satellites also widely used this global temperature and climate monitoring. And also we know that apart from those, we can use drones also, provide high resolution thermal infrared data for farms and construction site for a small area. As our customized area, we can use drones also. And thermal infrared data can be used for uh, urban heat island studies to identify the hot zone in cities. So this can be used for identify the hot areas in the cities. Surface temperature monitoring for climate and weather studies. Fire detection, volcanic activities, and geothermal energy exploration. We can use these thermal sensors. Those are basically the fire detection, volcanic activity, geothermal energy exploration. Those are for the satellite remote sensing, and some this one urban heat studies. Maybe you can use drone the drone thermal images also for those studies. So when we compare those three sensors, multispectral, hyperspectral, and thermal sensors, so the final comparison is multispectral has 5 to 10 broadbands, use reflected sunlight. It is ideal for land cover classification. We come to the hyperspectral, it's 100 plus narrow bands detect precise material properties. So it is suitable for minerals, uh, mineral identifications like that. In thermal infrared sensors, measure emitted heat used for temperature and water stress analysis. So, so those are the things I want to discuss with you today. If you have any question, you can ask now. Okay, I will upload this uh, presentation, and you can also see these videos. I also uploaded some materials for you to further study your reference material, so you can go through and get some idea about how these three sensors can be used in remote sensing. Since you don't have any question, I will conclude this lecture. Thank you very much and have a nice day.